Okay, thank you all for staying until today. And with these lives, it feels like one of these uh, post-credit clips after a Marvel movie or something. I mean, it's not going to be that exciting, but okay. So I'll be talking about functional role bonds. And this is more like in the border of arithmetic complexity and Boolean complexity. And I mean, it's just a first step towards trying to connect the lower bounds in arithmetic complexity and Boolean complexity. And what I'm going to describe is joint work with Michael Forbes and Mrinal Kumar. And we hope to upload it soon. Yeah. Okay, so let me motivate the problem. So far, we've been looking at lower bounds in arithmetic circuits of the following form. So far, it's been things like, so if a circuit C computes a poly f, some sort of hard polynomial, then C must be big. And we did a lot of examples of where the circuit C was in some restricted class and for some notion of big and so on. And one thing that was always a very recurrent theme in all of arithmetic circuit lower bounds is that when I actually mean computes f, we were always thinking of computing f in a very, very syntactic fashion, in the sense that it's not the function that you're interested in, but you're actually trying to compute it as a list of monomials. And this is what you want to do. Okay, so this is what has been happening in the arithmetic circuit complexity. And often when you look at Boolean complexity, so there is often a notion of arithmetizing your computation. Like, for example, whenever you have an OR gate or an AND gate or something, you replace them by products or whatever have it. And the goal of doing this is to make sure that whatever function you're interested in, this is really a function on just, it's a function on the Boolean hypercube. And you're trying to model this as a polynomial. And in such regimes, you're not really interested in computing it syntactically, but you're really interested in computing the underlying function. So the goal in this work is trying to answer questions of the following sort. So sort of somewhere in the middle is questions of the following form, where suppose f is a, okay. Suppose C is a circuit computing f functionally, can one say C is big? So what I mean by this is this. So one polynomial that we kept looking at was this Nissan-Wigderson family of polynomials. It's not relevant what it is, but it's a sort of generic hard polynomial which seems to be pretty useful when it comes to proving lower bounds for arithmetic complexity. But can we make statements of the following sort? I take a depth-4 circuit of bounded bottom finite or whatever, and I'm not really interested in computing the Nissan-Wigderson polynomial exactly, but I only care about whatever the circuit C computes, I want its values to agree with NW on 0, 1 to the n. Now, if C was multilinear, functional equivalence is exactly the same as syntactic equivalence. So there is nothing new that's happening. But C could potentially be a non-multilinear polynomial, in which case having higher powers could be useful and so on. But we would like to see statements of this sort. I mean, it somehow tries to connect them. We won't quite answer this, but we'll try to answer questions which are close to this. And let me try and give some motivation, which was also alluded to in Mrinal's talk, and I'll get back to that. But let's look at, let me just remind you of Ryan Williams's the ACC lower bound for those. Okay, let's just look at what happened in the ACC lower bound. This is an oversimplification, but this is roughly what happens. So you first start with an ACC 0 circuit. Okay, by ACC 0, it's a constant depth circuit where, unbounded finite gates, but you have, let's say, mod 6 gates thrown in. So these are gates that are going to fire if the number of inputs is exactly divisible by 6 or something. It's not that important, but you start from an AC 0 circuit and you reduce to something that is called the symmetric function of ANDs. Okay, and this is an old result of Beagle and Tarui. So this is roughly what happens. You start with an AC 0 circuit of, say, size S, and then you show that this can sort of be represented as a circuit of the following restricted form. You have a bunch of ANDs of literals. So you have a few of them, and then you apply some symmetric gate on top of it. So maybe you want to think of it as, let's say you apply a majority. It's not quite a majority, but something. And he said that there is, given a size S circuit, there is a fairly small sim of AND circuits that computes the same Boolean function functionally. Okay, let me throw in a few more parameters. Each of these ANDs turns out to be something like log S, if I remember. Sorry? There is only one symmetric gate. So you compute ANDs and then you look at the number of ANDs that fire. Depending on that count, you will decide to accept or reject.
The question is whether the reduction fixes in advance the symmetric gate, or is it?
Yeah, depending on the size. Whatever the size is, there is.
No, not the fan-in of the symmetric gate. Is it one symmetric gate?
No, it depends on the circuit, I think.
I see. But I think you can make it.
Yeah, you can make it.
But that's a different work.
Oh, that is Allender-Gore, I think. Right? Okay, good. Okay. Yeah, but for now, think of the symmetric gate as, let's say, being majority. It just makes life easier. So the symmetric gate is something, and the symmetric gate, the only thing that you get out of this is that this has fan-in something that looks like S to the log S. So it's not polynomial size, but it sort of gives you a reduction from a size S circuit to a quasi-poly in S sort of restricted circuit. And then he did circuit SAT faster here, and so that was, but this was a crucial reduction here. But here is an equivalent way of looking at such a polynomial. Okay, an AND is nothing but a monomial. Every AND I can just think of as a product of variables. Okay, and the sum of these monomials is basically going to tell me how many of these ANDs fire. Okay, how many of these ANDs are going to be 1 and how many are going to be 0. Now, depending on this count, I need to decide whether to accept or reject. So all I need to do for this is just basically write down a table that says, okay, for value, if it takes value 42, I'll accept, everything else I'll reject, or whatever. I mean, so some sort of table like this. And this is just some univariate polynomial that I apply on this. Right? There is some univariate polynomial which sort of just interpolates as to what sort of counts are valid and what are not valid. And I'm eventually just going to apply a univariate polynomial, right? Now this looks a lot like an algebraic expression, right? So what really is this? So a univariate polynomial is a sum of powers, right? It's a sum of powers, and because this fan-in is like S to the log S, for all I know, this power, I mean, the degree of the univariate could be as large as S to the log S. Okay, and what you have at the bottom is sum of products. Okay, so this is like a sort of a depth-4 circuit that we have seen often in the boot camp and so on. There are a few problems. Firstly, this should alarm people. I mean, this is like a heavily non-homogeneous circuit that we are dealing with. But let's just say that, so far, homogeneity seemed to be a pretty useful thing that we had in arithmetic circuits. We don't know how to get around with it, but let's just assume someday later, we'll be able to prove lower bounds for even non-homogeneous things. So let's be wishful and say that, okay, let's say this is not a problem.
Sorry, I'm slightly confused. Where is the power coming from?
because it's a univariate is a sum of powers of things. So that's where the power comes from. And yeah, so let's assume that this is not a problem. It is, but let's assume it's not. But the thing I want to point out is that, huh,
Why, I mean, if you just consider syntactic computation, why is it a problem?
no, I mean, you're proving lower bounds on this. I mean, if you want to prove lower bounds on ACC,
Yeah, for functional, but like just from a syntactic point of view, we can prove lower bounds for this even in the non-homogeneous.
Yeah.
It's highly non-homogeneous.
right, yes, good. But for now, I just want to completely ignore. I mean, the results that I'll be mentioning here will deal with homogeneous circuits of this sort. So I just want to brush that under the rug. But yeah, that's a good point. Okay, so but the point I want to make is that this reduction is meaningful only in a functional sense. You're finally dealing with a finally dealing with a boolean function as ACC, and you just came up with a different representation on this. So if the goal was to prove ACC lower bounds, the sort of lower bounds you want to prove is things of this sort. You want to say, okay, here is some function, and I want to say that any circuit that computes it which agrees with this polynomial on 0, 1 to the n, I mean, the circuit has to be large. There are various other things. This also has this nice property that on 0, 1 to the n, when I evaluate this polynomial, I end up getting a 0, 1 value. But for now, let's just try to relax the arithmetic circuit lower bounds. Instead of just saying that I want it to syntactically compute it, I want to sort of relax this problem and say that suppose I just know that it agrees with 0, 1 to the n. Is that enough for me to give a lower bound? And that's what this talk is going to attempt to do. And I'll spend a few minutes on why the typical techniques don't work. This was alluded to in Mrinal's talk, but I'll maybe say a bit more about it. So I hope the goal is clear. We're not going to achieve this, but we're going to take a first step towards it. Okay, this board was harder to erase. So. Okay, let's start with the first lower bound that we really saw in the bootcamp, which was this lower bound for depth-3 powering circuits. So we were interested in circuits of the following form. So this just computes something that looks like summation of Li to the d, where each Li is a linear polynomial. Okay. So this is sort of what we were doing. And the measure that we used for all these things was basically just look at the partial derivative space of this thing, and you show that for this it's small, for a polynomial that you're interested in it's large, and that was the proof. But let's look at what happens if you just change this functionally. Let's look at this really stupid example where you have x1 plus xn whole power n. Now this is trivially computed by a small sized depth-3 powering formula. But if I think of it functionally and I expand it, if I'm only interested in 0, 1 to the n, there is a unique multilinear representation of it, which is, I just expand it out, and whenever I see xi squared terms, I just reduce it to xi. This is what I'm going to do. But the point I want to make is that you will get one term, which is xn plus lower order stuff. Yeah, just think of everything as over reals, or whatever. Okay. So when I expand it out and reduce it mod xi squared equals xi, I have one monomial, which is the multilinear monomial, which is x1 through xn. And anything that involves squares and so on will now go to a lower degree guy. But the point I want to make is that the leading monomial of this multilinear representation is x1 through xn. Which means if this was my polynomial g, then the partial derivative space of g, this is like n choose k, because they're all going to be linearly independent. I'm going to get distinct partial derivatives. So despite this guy having a completely trivial partial derivative space, the partial derivative space here is just 1. But here you just go to exponential this thing. So just the fact that you agree on 0, 1 to the n is not enough to sort of translate this partial derivative based methods into a functional sense. Okay? And there are ways to get around this, and let me just highlight one way, and this was also there in Bentley's talk. which is instead of looking at this as your measure, you can now look at evaluation dimension as your measure. So I'll just mention, I'm not going to give the proof of this. So fix is that, use evaluation dimension as the measure. Okay, let me not go into the detail of this, but this is a sort of evaluation dimension and the Nissan's partial derivative matrix are the same sort of objects, but evaluation dimension is more useful in the functional sense as compared to the partial derivative matrix. If you work out things happen. Okay, so this is going to be the rough plan. I'll just state the theorem I'm going to prove. It's going to be a weaker form of what the question I asked for the class of depth-4 circuits. And we'll prove that, we'll basically show that there are some ways in which we could translate the lower bounds that we have already into the functional sense. This is going to be the thing. So are there any questions so far? Okay, cool. So let me just write down the theorem here. I don't think. Man. Okay, so let C be a homogeneous sigma pi circuit. Okay, computing a polynomial P. Okay, if P agrees with NW on 0, 1 to the n, I'm going to 0, 1 to the n, then C is large. I mean, rather C is big. Okay, so there's a lot of things which I'm hiding under the rug. So let me talk about the relatively minor things. So the first thing is, what does C being homogeneous mean? So I'm actually computing a polynomial NW, and let's say this NW is some polynomial. Okay, so is some explicit degree D polynomial on n variables. Okay. Yeah, think of it to be the permanent if you want. Yeah. So, or think of it as the iterated matrix multiplication, whatever polynomial for which we have lower bounds. Okay, so what the polynomial is will not be that important. So it's some degree D polynomial on n variables. And I want C to be homogeneous in the sense that the total degree is at most D. Okay, and so so this is one restriction. The other restriction I have is that this is something I would really like to get rid of, but I don't know how to. So C computes some polynomial P. If P was multilinear, this thing is trivial because functional equivalence equals syntactic equivalence, so it's trivial. But we are going to make a one step in the sense that the individual degree of P is bounded by some constant, say 100. The actual constant is not important, but I just want to say that if I finally expand the circuit C out, I get some polynomial P. This is an assumption I'm going to make on the polynomial, that the degree in every variable is not too large. Okay? Then this would work. So this is going to be the theorem. Ideally, you would want to get rid of this. Getting rid of this it looks a lot like trying to go beyond homogeneous for depth-4. This is something which is more of an artifact of the proof that I'm going to present. And
why is it like going beyond proof for homogeneity?
Because, I mean, an easier question would be that, I want to compute NW, but suppose I have a circuit which of formal degree not D but slightly bigger than D. Can you prove lower bounds there? That is an easier question. because here I'm only asking for agreement on 0, 1 to the n. So if you want to answer that, you would probably first want to answer the syntactic lower bound part. So this is the, yeah.
Isn't there something known about the relation between circuits who has powers, multilinear circuits, and circuits who has individual powers constant?
But relations in what sense?
It's the same up to polynomial.
I don't know of such a transformation. I mean, like, I don't have a concrete counterexample or something, but I don't have a transformation. Like if the question is, suppose I give you a circuit C that has low individual degree, can I extract out its multilinear part by small circuit? I don't have such a transformation. But I mean, I guess here he is interested in D being small, right? I mean.
Still, I mean, we know that depth-3 we have low bounds for multilinear, even if D is constant, right? I mean, okay.
Okay.
But I believe there should be a difference.
But the syntactic degree of the symmetric is n.
The traces.
So here by individual degree, is it a formal individual degree or is it?
No, it's the final. I mean, intermediate gates could compute higher individual degree things, and or like okay, all the proof will care about is what is the final individual degree of the polynomial P, not the circuit that computes it. Okay, so okay, I should have just said that C is a circuit of degree bounded by D. I mean, yeah, formal degree bounded by D, but individual degrees could you could blow things up and come back down or whatever.
You can compute x to the n and then cancel
Right.
x to the d and then
You could take x to the D and then cancel things out.
Yeah, okay.
Again, I mean, so this part is really an artifact of the proof, but I think, okay, so this sort of, I mean, to me, this is more along the lines of what Mrinal presented in the sense that it's a sort of evaluation analog of whatever we have been doing, and which is sometimes pretty useful because it sort of behaves well with algebra. And I'll try to give a few examples of why this is the case.
Can you repeat what you said now? It's an individual degree is P, but it's not the syntactic degree that is it.
So there are two things I want. One is from the circuit, and one is from the final polynomial. From the circuit, I want to make sure that the formal degree at any gate is D. That's the requirement I have from the circuit. From the polynomial, what I want is that I want the individual degree to be bounded. But this is not a requirement on the circuit. Yeah. Okay. Okay, cool. So the proof is going to be fairly simple. It's just going to be like, we know measures to do this in the syntactic sense. I'm just going to give you functional proxies for each of them. That's it. Okay. So, okay. There are no questions. What? Oh man. No, no, the other side was worse. I tried it. Okay, it doesn't say permanent. Sorry? It's a good one. Okay, cool. So this is what we are going to do. Okay, so I'm going to use gamma for the measures. And just to remind you, even if you don't remember what this measure is, there was this measure called the projected shifted partials. It's not important, but there was some measure, there were a couple of parameters K and L. And this was a measure that was used for proving lower bounds for depth-4 circuits. Okay. So this is, I'm going to use this notation to mean that measure. The actual measure won't be important. I'll be working with much simpler cases. And I'm going to define a proxy which is called shifted eval dimension. So I'll just write down, this is like projected partials. And this is going to be shifted eval dimension. Okay. And the point of this would be that shifted eval dimension will actually behave nicely when one polynomial is functionally equivalent to another polynomial, because it'll be defined only based on evaluations on 0, 1 to the n. That's going to be the main thing. And the proof is going to go in 2 steps. So lemma 1, okay, everything is for NW, but let's just pretend that we have a lower bound for permanent and keep doing this. For the permanent, we'll show that gamma SED so we'll show that this doesn't really change anything. And the only thing that I will need from the permanent is the fact that the permanent is set multilinear. What I mean by that is, like, if I think of each of the columns as separate boxes of variables, then every monomial picks up exactly one variable from each box. That's the only thing I will use. Okay. Lemma 2 will basically be for a polynomial P with individual degree at most, say, 100. So gamma K comma L of SED is at most gamma PSP of K comma L, not quite K comma L, but so this is what we would show. We would show that this measure will be, if I know that P has small individual degree, then there is some way in which I can relate the proxy that I have to the actual measure that we were dealing with in small circuits. The only thing that you need to believe from me is that this loss of K from K to 100K will be irrelevant when it comes to the depth-4 reductions. The depth-4 reductions typically tries to prove an n to the square root d lower bound. It's just that constant will become a little weaker now. That's about it. So basically these two will together let us prove functional lower bounds for depth-4.
So that's where you need the degree to be constant, right?
Yes, this is where I would need the degree to be constant. It is just to relate the measure that the proxy measure to the syntactic measure that we have been dealing with. Okay?
So lemma 1 holds for
Lemma 1 will hold for any set multilinear polynomial. So NW, IMM, permanent, determinant is good. Now lemma 2 will work for polynomials that have low individual degree. Okay?
And here the evaluation dimension, you're evaluating over the whole, not over 0, 1, right? You're evaluating
No.
the whole-
So
over the whole,
this will
like,
every end. So this will again be a rank of a big matrix. So this guy will be a rank of a big matrix where every entry will basically be an evaluation of the polynomial at some point in 0, 1 to the n. So as far as if f and g agree, okay, so maybe let me just write down. So one property that I will have, I'm going to use prop for this, is that gamma SED of f equals gamma SED of g if f and g agree on 0, 1 to the n. So this is a property that I would have. This would let me move from sort of functional equivalence. Okay, so
polynomial set multilinear if I have like every variable is a set in itself, right? So what does
Okay.
it mean?
So that will come into the definition of this. I'll give you, I won't prove this, but I will prove a weaker version of this. I will prove a much weaker version, but this is sort of how the lower bound proof would work overall. But I'll prove a much, much weaker version. Okay, and
Why are you going to use the fact that we use small polynomial?
so that's because I would eventually want to bound this for a depth-4 circuit. And I know this bounds because of work that was won prior, and that sort of bounds is known only for depth-4 circuits where the formal degree is bounded. So I'm going to use that proxy for my upper bound, and I'm going to use this proxy for the lower bound for my explicit polynomial, and that will give me the size bound. Okay? Okay, cool. So as we mentioned earlier, the real trick was really, partial derivatives is something that behaves very, very badly when it comes to functional equivalence. And I just want to present a proxy for taking partial derivatives. Okay? And this is. Okay, this is painful. No, let me try to use this board then. Okay. Okay. So let's take something like the permanent and okay, and okay, and so here's what I'm going to do. I'm going to restrict myself to taking partial derivatives of a very, very specific form. And if you have seen the depth for lower bounds, you will just notice that this doesn't hurt any of the calculations. What I'm going to do is I'm going to take a kth order partial derivative only from first k columns. So I'm going to do this by picking one guy from each of the k columns. And there are enough partial derivatives for the calculations to go through. Sorry? Yeah. So I better pick it up in distinct rows and distinct columns so that the partial derivative is non-zero.
So that's where the set multilinear.
So this is where set multilinear is going to come. Now I want to achieve the same operation of taking partial derivatives, but I don't want to take partial derivatives. And what you should do in this is like pretty obvious. Let's say I'm interested in the partial derivative with respect to, let's say, the first k variables. What is a proxy for this? I just set those k variables to 1 and set the rest of these k columns to be 0. So the resulting polynomial that I'm going to end up getting is exactly what I would get if I took the formal partial derivative with respect to these variables. Okay? So far I had not defined what shifted eval dimension, etc. are. This is what is going to be. So the variable x are going to be partitioned into y and z. Okay? And I'm going to look at things of the following form. So I'm going to so A is going to be a restriction of just the variables in y with the property that I'll just make sure that k of the A variables are going to be set to 1 and the rest are going to be set to 0. Okay. So this is what I'm going to. So yeah. So A is going to be in 0, 1 to the size of whatever, the size of y, whatever that thing is. Okay. This is going to be my proxy for del equals k of p. This is intuitively what you should be looking at. Again, now this is still a formal polynomial, but I'm now going to look at the truth table of this. Just think of it as, look at its evaluation on all of z. Okay? So, and you take the span of these. This is going to be the. Can I write on this? Will it work? Okay.
So essentially what
to a particular substitution.
Yes, so this is what I want to say.
Even after shifts, they
So-
remain to be the dimension does not change.
So the only problem, so whenever you're multiplying by a monomial or something, you can still think of it as a polynomial and evaluate it on all of 0, 1 to the n. That is something you can always do. It's just that partial derivative is not an operation that has a functional analog. And for polynomials that are set multilinear, you could sort of replace partial derivatives by these partial evaluations. This is all that I'm doing so far.
So when the statement is true even for like partial derivatives.
This is true for partial derivative. The shifts is not going to make a difference, which is why I didn't want to explicitly define what ACD was, but it's just good to keep in mind that, let's say your measure was just partial derivatives. Now, if you replace partial derivatives by partial evaluations, everything will just work out for set multilinear polynomials. You haven't changed anything. The catch is just this guy, right? So I want to make sure that, P is a polynomial that could possibly have large individual degree. Now I want to make sure that I haven't lost too much. So here is a claim. So I have some, okay. So I have some x which is y plus z, which is some partition. I'm looking at partial derivative with respect to y of order at most k. Okay, this is what I'm going to do. Okay. So the claim I want to make is the partial derivatives of a polynomial p of order k. These are formal partial derivatives. I want to claim that they are no, sorry. Oh God. These partial evaluation polynomials, I want to claim that this is contained in the span of partial derivatives of p of order kr. That looks like Israel, right? So this is what I would want to say. I want to say that let's look at partial evaluations where we are going to set the y variables to something. Okay. Any such partial evaluation I want to claim is in the span of formal partial derivatives of p. R is going to be the individual degree. So in this case, this is my R. And I could put 100 everywhere, but it'll just make it messier. Yeah. Okay. So, and the proof of this is just Taylor expansion. I mean, all I want to do is I just want to expand P around Y and set that to A. And I'll just look at what are the terms that I get in the Taylor expansion. Okay. So here's the proof. So let's look at P of, okay, the Z variables are not that important. Let's just throw the Z variables in the thing. I'm just going to think of Y as being the variables of interest. Okay, by Taylor expansion you get that this is, okay, this is a sum over all exponent vectors times the partial derivative with respect to E of P evaluated at Y. Right? So this is just, I've just written Taylor expansion. I've probably dropped a few constants, but I don't care about those things. Okay, so this is the thing. Now I just want to look at this, such a term, and figure out what are the terms that survive in this Taylor expansion. Here are the things that I know. I know that the individual degree of P is bounded by some R. This is one property that I have. The second property that I have is that A is a point that has at most k ones, the rest are all zeros. These are two properties that I have. Now from this, what can I conclude? So I can conclude that if this exponent vector, I mean, if I'm taking a monomial on the A's that involve more than k guys, okay, more than k distinct guys, then I mean, then it will, this a power e is going to evaluate to 0. So what I mean by that is if I look at the exponent vector and look at the number of distinct a's that it involves, if this was greater than k, implies a power e is 0. So this is one bound that I have. Okay. The second bound that I have is that p is a polynomial of individual degree at most r. So how many times can I differentiate a single variable? If I differentiated more than r times, then this formal derivative is going to become 0. Okay. So this says that, okay, let me just, because p has individual degree at most r, I know that the L infinity norm, which I mean by the maximum coordinate is that if this was greater than k, then this is equal to 0. So which means there are not too many e's left which can help you. So first thing, that the number of distinct coordinates in E can be at most k, and each coordinate can have degree at most r, which means all these guys are going to be in the partial derivatives of p of degree at most k times r. And that's it. So this says that whenever I know that p has individual degree bounded, then each of these partial evaluations can always be expressed in a linear combination of these partial derivatives. So the way you should think about it is like, now if I knew that the linear combination of these partial derivatives, they don't span too large a space, this tells me that the set of partial evaluations of p don't span too large a space. And now multiplying by shifts and taking truth tables and all is not going to change anything. So once you have this, I mean, it should be clear that, if I just replace, let's look at our projected shifted partials or whatever we were doing, instead of taking partial derivatives, if we look at partial evaluations, the upper bound does not take much of a hit. And the lower bound doesn't change at all for the polynomial that you're interested in, because the polynomial is much nicely behaved. So these together with what we have seen so far will basically tell you that whatever lower bounds you had for that, as long as you could tolerate this factor of r times k, I mean, things will still work out. So this is more or less, I mean, this is basically the proof. The proof is, of course, really, really simple. But I mean, so I really like this intuition of sort of, so something that was, to me, was unsatisfactory about projected shifted partials is that going modulo xi squared equals 0 is a terrible sort of operation because it doesn't behave well with polynomials. Because you're just taking a bunch of non-multilinear monomials and just setting them to 0. What Mrinal described in his talk was actually that, you could instead go modulo xi squared equals xi. It gives you exactly the same sort of behavior, but is in some sense nicer because you can now think of them as evaluations on the hypercube. It makes sense with these evaluations. And this is just pushing that intuition a little further. And of course, there is a lot of things to be done. I mean, first thing is, I don't know if the individual degree bound, I mean, this is clearly an artifact of this proof, but we would really like to get that removed. We don't know how to do that. And sure.
Over here you have done it for multilinear polynomials.
Yeah.
The same thing you did for individual degree.
So, okay, so there are two steps. So whenever you prove a lower bound, you would be doing this in the following sense, right? You first have a circuit model. First you build a measure. And then you first show that for the circuit model you're interested in is you have a good upper bound. For that, lemma 1 is not important. It's only lemma 2. You use lemma 2 to say that this is the measure I'm interested in. Here is an upper bound for this measure. This has already been calculated by prior work. So this is going to be your upper bound. The next step is to come up with an explicit polynomial for which your measure is very big. For that, lemma 1 is going to be important. I just wrote it for the permanent, but you need to write it for whatever polynomial you have a lower bound. So it's not really permanent, it's going to be IMM or something, IMM or NW, but
Maybe it's just helpful to just for the audience to state this open question for like sums of powers of quadratics.
right.
Just any functional lower bound.
Okay, so here is an open question. So for the class of sums of powers of quadratics. Okay, by this I mean these are expressions of the following form: qi to the d over 2, where I going from 1 through s. Okay, can we prove a functional lower bound? It would be nice if you can do this without any individual degree blah 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 requirement. So this is I think the simplest model for which I don't know what the answer is. So just I mean maybe an exercise is that try to see if the eval dimension based methods, does it give you a functional lower bound for say homogeneous depth-3 circuits? It's a nice exercise to try. Anyway, I'll stop here.
Yeah, so when you're looking at the multilinear expansion, it's like doing Fourier analysis on the cube.
Right. Yeah.
And there you do this concept of the directional derivative or the Laplacian in a certain direction, which corresponds to the derivative.
So this proof, which the way Ramprasad described, it's done using shifted evaluation dimension, but you could also think of this as taking additive derivatives, which
Yeah,
is what you're saying. It's just much nicer, like from an arithmetic circuit point of view. To think of this.
But yeah, but you could just replace these derivatives by just f of x plus a minus f of x, sorry, f of a, and the thing would just work out. Yeah. Okay.